Hello. In this lecture, we are going to continue our discussion about AVL tree data structure. And in this lecture, we are going to discuss its implementation. Okay. So in our textbook, it is in the example of Java AVL tree. Okay, there are two files, the AVL tree class definition and the driver for the AVL tree class. And so here is AVL tree definition. So we already discussed, we have the instance variable root, and it's a bin node. And for the bin node, we have a new instance variable height. Okay. Okay, and this is a default constructor, nothing new, like the BS tree, binary search tree, and it is empty, nothing new. And we have this new method height to find the tree height. Okay, so it's the height for the root node. And we also have the function, the method for each node's height. Okay, so it will return the node's height unless it is a null node, then the height is -1. Okay, and for the search function, there is nothing new, okay, compared with a binary search tree. And we also have a instance method balance factor. So it's a height difference of the left and the right child, okay? And here is a definition for the right rotation and the left rotation, okay, regarding a node, okay. So you can see we need to update the left and the right child, okay. We also need to update the respective height, okay. And what is the rotation? The return, it returns a new node that so this is rotate right, similar for rotate left implementation. And then here we have the balance for each node, okay? And the return is also a bin node, if you recall, because for each of the 4 cases, a node, if the node need to be balanced, then it will be swapped basically with another node. So in the implementation, we need to check the balance factor and then do right rotation or left rotation. And if it is the left, or right, then just one rotation. Otherwise, you need to have 2 rotation. Okay. So this is for the balance, node balance. And then we also have the height, update the path height. Is it? Yeah. So for a specified, so for a path, is it? And we get the specified node. Okay. You try to get the node, and then you're going to update its height. So this is mostly for insertion, if you recall. when we do insertion, insert a new node, we need to update the height. And the balance, the path, okay? So the path is stored in an array list, okay? And we do bottom up balance, okay, for each of the node. So from the path, we get the node, is it? And then for each node, we update the path. We balance, and then we also update the path. And then here is a regular insertion. So nothing new for the insertion part. So you do need to find where you're going to insert. After you find it, you create a new node with it and connect with parent node. But then we need to update the path height. Okay, so here is a path. And when we do insert, so here is the new part. So we insert. If we take a close look, okay. So for the insertion, we add the path. It's an array list of the bin node, okay. So whenever you have we start from the root node. Start from the root node to do the search, okay, to find the item, to try to find the item, is it? And before we find it, then we add each of the node along the path, okay, to the path, to the array list, to keep the log of all of the bin nodes along the path. And after it, so after we insert, then along the path, we need to update each of the nodes height, okay? And then we need also do node by node balance along the path, okay? So this is for the insert operation. And if you recall, we also discussed that we can also implement the insertion using recursive implementation, okay? In this case, we have a utility function called insert node, okay? To insert an item, we start from the root node to try to insert at its location. So we call insert node. And this insert node is a recursive implementation. Okay, and if we take a look, we will see, okay, so if you reach the leaf node, then definitely you're going to add the new node. If the item already in the tree, then because AVL tree, each node is unique, okay, it doesn't allow duplicate values. And so if it's less than 0 in the comparison, so item is less than the current node, you insert to the left. Otherwise, you insert to its right subtree. Is it? So here we do the recursive calling. Recursive calling. So you call it self. Is it? And after that, after you insert, then you need to update each of the node. Is it? So here we do the update. And we also need to balance. Okay, so this is a recursive implementation. So basically, the height updates and the balance will be the rollback when you do the recursive call. Okay. So over here we don't need a relist to keep track of the nodes along the path, okay, because it automatically will be kept when we do the recursive call. Okay, and then let's see for the delete. Okay, so delete similar the previous implementation compared with the binary search tree. Okay, so we find the node and then we do delete. Okay, so after we do the delete, then we are going to try to find the path. Okay, so find the path. So to the node and or to the parent node. And that we find the path. After you find the path, then you need to update and update each of the nodes height and then do the node balance. Okay, just like the insertion. So this is the iterative way for the delete operation. And then what next? Here is a get pass. Do we have the get pass or the delete? Yeah. So in the delete, we call the get pass. Okay. To find the whole path. This delete is not like for the insertion. When we do the search, we just record the path. Okay, because for the delete, the situation is more complicated. So we do the deletion first and then go back to find the path. Okay, we call it get path. The get path, same thing, they use an array list. Okay, so basically it's just do the search, but at the same time, they keep a record of the path, the search path. Okay. So this is for the get path utility function. And then we can also do the recursive way implementation for the delete. Okay, so delete an item, and we call the delete node and plug in from the root node. Okay, for the specified item. And this delete node method, this is a recursive function, okay? So same thing, if the item is less than the current node, you plug in the left child. Otherwise, you call the delete node plug in with the right child, okay? Or you just find the item and start to do the deletion, okay? And there are some other case, if you recall, when we do binary search tree for the deletion case, and we need to find the next in order and then do the deletion. That's a little bit of more complicated cases, okay? So here we also have utility function next in order and delete next in order method, okay? After that, we also need to do the height update and balance, just like insert. And here we can also see the next in order is also a recursive call, okay? And then for the delete, next in order similar, okay? We do the recursive call and at the same time, we also do height update and node balance. Okay. So this is a recursive implementation about delete operation. And for the in-order, pre-order, and post-order, it's actually the same for the traversing, okay? As a binary search tree and level by level search and recursively do the traversing, okay, all the same as the previous. And so this is the AVL tree class. And then in our driver, what we did test is we have a sequence of numbers that we try to use to build the AVL tree, okay? So we just keep call the tree insert, okay? And then we can do the in-order, pre-order, and post-order traversing, okay? And we also output the whole tree, okay? So here is the output, okay? And we also document for each of the insertion, if there is a balance, we are going to do some output, okay, for our balance operation. And then we also do some delete operation here. So you can input a value and do the delete, okay? And after that, we can output the tree. So here we did test it. So the tree, okay, you can check the tree. It's a AVL tree. And then we say, okay, we want to delete 62 from the tree, okay. After we do that, it's not in the tree. And we can clearly see the tree is a AVL tree. Okay, so that's about this example. So in our next lecture, we are going to move to another topic. Okay, see you.